Hello and welcome to Late Night Code. My name is Ian Riley and I'm excited to be bringing you another video. So we're finding some time in the afternoon on this very lovely Memorial's Day to try to get caught up on our recordings. Today we're going to be presenting the problem Sun and Moon, which is another easy problem from the North American Regional Contest that took place this last February. It's rated at a 1.9. After this problem, we'll be moving on to the next one, which will also be the last easy problem from that contest. And then we'll get to start working on medium difficulty problems, which is really exciting. So I'm really looking forward to getting there, and we probably will be able to get there very, very soon. So pretty cool. But with that out of the way, let's go ahead and jump into this problem. It's called Sun and Moon. You recently missed an eclipse and are waiting for the next one. To see any eclipse from your home, the sun and the moon must be in alignment at specific positions. You know how many years ago the sun was in the right position and how many years it takes for it to get back to that position. You know the same for the moon. When will you see the next eclipse? The input consists of two lines. The first line contains ds and ys, where ds is how many years ago the sun was in the right position, and ys is how many years it takes for the sun to get back to that position. The second line contains dm and ym, where dm is how many years ago the moon was in the right position, and ym is how many years it takes for the moon to be back in that position. We have to output a single integer, the number of years until the next eclipse, and the data is given such that there's not currently an eclipse, and the next one will definitively occur or definitely occur within the next 5,000 years. Okay, let's go ahead and kind of summarize that back. So the way we can kind of think about this problem is we effectively have put out a telescope, we're pointing it at a specific position in the sky, and we know for a fact that there's going to be an eclipse at this position in the sky within the next 5,000 years. And the data that we have is that we saw the sun at this position ds years ago, and we know that it takes ys years for the sun to come back. We also saw the moon at this position dm years ago, and we know it takes ym years for the moon to effectively come back, right? And so what that means then is that based off of these two offsets and the cycles or rates at which they go through a full loop, we have to figure out at what point in time will they both line up on this position that our telescope is pointed at. This is actually a fairly straightforward problem once we get the right mental model of it, because what we can do is we can actually start with time 0 and just keep moving ahead in time and then ask ourselves if we currently have an eclipse, because the number of time points is only 5,000, so that's really, really easy for us to crank through. I do kind of want to use this opportunity to talk about something interesting though, at least something that I find interesting in programming, which is modular arithmetic. This is a problem that can really benefit from at least a basic understanding of modular arithmetic. There's also a really, really cool optimization that we can make to this problem in certain cases, not in the general case, but in certain cases. We won't be looking at that today, but that might be a good topic for a bonus video because, again, there's some really, really cool things you can do with modular arithmetic. With that out of the way, let's go ahead and just jump over to Excalidraw and start talking about this problem from the perspective of modular arithmetic. Now, let me lay out the details of the problem just real quick. So we know that we're given the following variables, ds, ys, and dm, ym, okay? With that, let's go ahead and talk about what modular arithmetic means. Modular arithmetic is typically written in the form a congruent to b mod m. In programming, this will also be written as a double equals b percent sign m, because the percent sign is the typical operator for modulus. And what this will give us, or what mod will give us, is the remainder after division. So another way that you can think about modulus is if we were to take b mod m, we want to know what the remainder is after dividing b by m. And so that's another way of saying that b is equal to some k times m plus a, right? So b is equal to some factor, some natural number factor multiplied by m plus a. And so if we were to divide b by m, okay, then right now m can only go into b k times. And so if you were to think about this as being the floor of or integer division, that would be equal to k, right? And then there would be some leftover fraction, okay? And that leftover fraction represents this value a divided by m, okay? And so again, mod always gives you the remainder after division. It's going to give you that target number there. So that's its purpose. It has a lot of really cool uses. One of the really cool aspects of modulus is that modulus always gives you some value a, where a is greater than or equal to 0 and less than m, strictly less than m. So for example, if m were to represent the length of an array, you typically have to be worried about out of bounds exceptions by having a negative number or having a number that is equal to or greater than the bounds. But with modulo, you can never produce something that's out of bounds because it must be strictly greater than or equal to 0, meaning it can't be negative. And it also can't be equal to the bounds or greater than the bounds. So a modulo will actually keep indices in bounds. That's a really cool side benefit of modular arithmetic. The other thing that modular arithmetic can really help you with, which is relevant to this problem, is factoring for cycles. When you have a rate at which something occurs, then you can figure out effectively whether or not a point in time, you can effectively group all of the points in time along that cycle into different categories and then determine if the current time falls into one of those categories. So I think that's the better way to explain it. So for example, if I have 100 years and I know that the sun, we go look at the sun real quick, I know that the sun takes ys years to complete a cycle, then effectively what I can do is I can take my 100-year length and start breaking them up to or partitioning them into different categories for the sun, where those categories represent individual points along the sun's movement. And so that means then is that if I were to take the sun's rotation, okay, and we were to say, for example, right here at the top is when the sun is kind of at that point that our telescope is looking at, then ys effectively breaks up this rotation into ys points, okay? And so that's ys points. And so then if I have a 100-year span, then each of those years now get assigned to one of those points. And if ys is smaller than 100, then multiple of those years all get assigned to those points. So that's what modular arithmetic can do for you, is it can allow you to take some quantity or some length, if you will, and then partition them into categories. It also means that the mod value, which is again remainder after division, actually takes on a new meaning as well. The other meaning it takes on is what's called a modulo class or mod class. It's not proper in most cases to think about a mod class as being a quantity. Okay. We'll dive more into that in a later video. I don't want to go too deep in the weeds with mod, but that's just to say that you want to think about mod as being like a target on a circle or a point on a circle, rather than thinking about as a measured quantity. Okay, rather than thinking about as a measured quantity. So B and M in this case are measured quantities. M is the length of a cycle. B is effectively the length of your line or how many years you've counted or things like that. And then A is what class or what point on the circle does B go into given the length of that circle. Okay. Another way to think about it would be to say that A tells you where on the circle you are. B tells you how far you've run in total, okay? But if you look at a point on a circle, like if you're watching a NASCAR race, you know where they are on the circle, but you don't necessarily know how many laps they've taken unless you actually look at the board, right? So that might be another way to think about it. How does that help us here though, right? So let's, I don't want to go too deep with this. This is the academic side of me coming out. I could talk forever about even just the basics of modular arithmetic, but how does this help us with this problem? Well, based on the values they've given us, we have a few interesting details. We know that ds is how many years ago the sun was at the correct point, which also tells us that ys minus ds is equal to the number of years until the sun is at the correct position. And we can go ahead and call this ps, okay? We also know that the same is true for the moon, ym minus dm, which will be equal to pm. So this is the point in time in which the sun is at the correct position and the point in time in which the moon is at the correct position, but they may not be the same points. Okay, if they are, then we have an eclipse at that point, but if they're not, we'll have an eclipse at some other point. And that also then tells us that we're going to have an eclipse if we can determine the following factors. So if we can find PS plus KS times YS, if we can figure out what K is, we can have that be equal to PM plus KM times YM. And again, we would need to figure out what that KM is equal to. And these are effectively equal to our solution, which we'll call X. So what's going on here? Effectively, since PS is the next point in time in which the sun hits our telescope, and PM is the next point in time in which the moon, right, comes in front of our telescope, then they now have to cycle around by YS and YM, right? Every that many years, they'll come back to that point. And eventually, given a certain number of cycles for each of them, we'll have them both be lined up. And that's the year in which we'll have an eclipse. Okay, so if we can solve for KS and KM, then we actually know exactly when we'll have an eclipse. Okay, so that's effectively what we need to do here. Now, how could we figure that out? Right, well, a very basic way that we could figure that out, like I said at the beginning, is you can just start with some time point t0, move to t1, and then just keep going all the way to tn, where n has to be less than or equal to 5,000. And you can keep just checking whether or not this time point will satisfy this particular formula. But how would you know whether or not the time point is a proper solution, right? Whether or not there's a KS and KM that would give you this time point. Well, a very easy way to think about that then is to think about time as being the car in NASCAR that's running. Am I doing a right-hand circle? Okay, I'm not going to worry about that, but it's the one who's actually driving the loops here. Okay, and so that's the way that we can think about it. Now, how would we know then whether or not this time point, right, is at the proper position in this loop? Okay. Well, the way we can do that is with mods. If we look at PS and PM, we can look at those as values, meaning the number of years until we hit the sun and moon being in the correct position. But they're also modulo classes. They represent a point along that circle. Okay. And so if we can find some TI where it is the case that PS is congruent to TI mod, and this is going to be YS, and some PM congruent to TI mod YM, then what that means is that there's some time point in which, given the length of the cycle of the sun, right, we're now back at the exact position in which the sun is in front of our telescope. And then again, that point in time, mod YM, means that it's repeated enough of these cycles of the moon to now be at the exact position where the moon is in front of our telescope. And if the same time point satisfies both of those conditions, then that means we have an eclipse because both the sun and the moon are in those proper positions. Okay, so that's how modular arithmetic can help us. We can basically just ask the question, does TI mod YS equal PS? And does TI mod YM equal PM? And if they are both true, then we have found the year in which we have an eclipse. And we just find the first one where that's true. That also allows us to do one very simple optimization. Rather than thinking about going from T0 to T1 to T2 and so on and so forth, because of the fact that they can only come back to this original point every YS or YM years, we can actually start with one of the two values, PS or PM, and then just keep skipping ahead by YS or YM respectively. Because again, those are the years in which one of the two sun or moon will come back to that position. You don't need to check all the points in between because they wouldn't be valid for that respective body, for that respective sun or moon. Okay, so these are some very basics about modular arithmetic, but they can help us with the testing of these particular time points to help us actually produce a solid solution and get slightly better than just checking 5,000 arbitrary points. Okay. Now, there's another really cool optimization that we can do here with modular arithmetic. However, it doesn't work in the general case, so I'm going to save that for a video later in the series. But with all of that out of the way, let's just go ahead and jump into Alacritty and actually start solving this problem. A couple of other things, and I'm going to cover this in a later video, but I've gone ahead and added a few standard in helpers to my template. This is actually, when I wrote these, I was just it just blows me away sometimes how amazing the Rust trait system is. So these are effectively helpers that can help me to digest standard input into shapes that I prefer to use, like single values, vectors, and tuples. But I can actually set them up to be inlined, so that way there's no performance overhead at all incurred by using them. And now I don't have to keep messing around with buffers and clearing them and trimming them and parsing them and all that stuff. I can now just call these inline functions and just get the shapes that I want. So pretty awesome. An example of that would be to, we're actually going to look at it now. Our first inputs are always going to be ds and ys. So what I can do now, rather than kind of creating my buffer, reading into it and all of that, is I can just say let ds ys be equal to next tuple turbo into, and then we'll just say u size in this case. We're going to use them for modulo categories and indices, but we're going to be using them over ranges. This is fine. And then we can now just say and pass a mutable reference to a string new, and then just close that off. And now we have our dsys tuple, right? And we can just do that again, and this will be dm, this will be ym, and there we go. So now we've just read in two tuples. If we want to be slightly more efficient, I can allocate a buffer beforehand, pass in the buffer, clear it, pass it in again. I'm not so worried about in this case, but that just makes the solution so much cleaner now, and I love it. So, and again, these are all inlined, so we're not actually even calling another function to do this. Rust will just replace that when it compiles. So super, super cool. Okay, so now the next thing I want to go ahead and do is calculate my ks and km, where my ks here is going to be equal to my ys minus ds, and the km is going to be equal to ym minus dm. So that's going to be the point in time in which we come back to these. Then the last thing I need to do here is go ahead and set these up to be mod ys respectively, and and then mod ym respectively. Okay, cool. So now we actually have the length of time until we hit these points. Sorry, we were calling these PM and PS respectively. So now we have those points and we have them as a part of their appropriate mod category. And then I can just go ahead and say let t, which will be mutable here, let mut t be equal to, and we'll just have it be PS. And then we can just say while t is less than 5,000, and in this particular case, t has to fail one of the two categories. So you would say t mod ys is not equal to, ys is not equal to ps, or t mod ym is not equal to pm. Okay, so if t is greater than 5,000, we would, or greater than or equal to 5,000, we would break. If t is not, if t is in the ps category and in the pm category, then it fails on both of these conditions, and since it's a logical or, it would fail entirely. We'd have a false term and break out of the loop. And so then the last thing we do is we just say t plus equal, and then in this particular case ys, since we're using it over ps, and then afterwards we've found our solution, so then we just go ahead and print t. Okay, so looks pretty good. We get our sun pair, our moon pair. We know the point, we know the mod class for when the sun and moon hit the respective point in the sky. We'll start with PS and we'll check if that point is a solution. And then if it's not, we'll keep incrementing by ys until we find an appropriate solution. Okay, that's looking pretty good. So now let's go ahead and just do a quick cargo run, and then we'll pass in our solution for sun and moon. Okay, and they told us it'd be 310, 1, and 2. Let me go ahead real quick and we'll just clip dash p and then cargo run -- sun and moon. Okay, and we get out 7. 7 is supposed to be the answer. And then now let's go ahead and quest sun and moon. I already installed the data, and passes across the board. Okay, and there we go. We've passed all of the test cases on Caddis, and we have another ICPC problem knocked down. Okay, so I hope they enjoyed this episode. I hope that the sort of discussion on modular arithmetic was a little bit helpful. Mod can be a very interesting and also sometimes confusing topic. There are some really, really cool advantages for understanding modular arithmetic well. So if you don't feel like that you do, please post some questions in the comments below. I'd love to answer them. Please do some research on your own to learn more about it. But there's some really amazing algorithms that we can use through modular arithmetic. Some of them have been around since, like 300 BCE, which is absolutely amazing that we still use some of these algorithms in our computers today, 2,300 years later, right? Really, really cool. So I hope that you enjoyed this and I look forward to having the next one. But until then, have a great night.